Thanks, Tool, and greetings, everyone. I'm Andrew Barton, Research Program Manager here at SmartSat CRC. It's great to see so many people here, many new names I don't know. I spend most of my time looking after our main research program, but it's great to be with you today for these three PhD talks. We have three great speakers covering three of the main areas of our research activity. So we've got Earth observation, onboard computing, and also advanced telecommunications. So looking forward to hearing from all of those. We're going to have, each speaker will speak for 20 minutes and we'll have 5 minutes of question time. I do encourage the different PhD students to take advantage of this time and ask your questions, and also maybe just say who you are as well, and what your PhD is on. Yeah, let's get started. So I'm going to firstly introduce speaker number one. Okay, so the first speaker is Jason Dail, who'll be talking about his project, which is improving detection of clearing and regrowth in woodlands using synthetic aperture radar. Jason is a PhD candidate at the University of Queensland. His project aims to improve woodland clearing and regrowth by using sub-canopy structural information provided by SAR. Jason did his bachelor's in geosciences and minoring in geospatial technologies at the University of North Carolina, Wilmington. And he holds a Master of Science in Geography of Environmental Risks and Human Security. So thank you very much, Jason. You've got 20 minutes.
All right. Hi, my name is Jason Dail. As Andrew said, I'm at the University of Queensland. I'm working on project P306S, improving detection of woodland clearing and regrowth using satellite imaging radar. What is the overall significance of my project? It is that the majority of Australia's forests are woodlands, and there isn't an accurate and reliably repeatable method for mapping and clearing regrowth. So just a bit of a project summary. The aim of my research is to determine to what degree can imaging radar be used for clearing and regrowth detection, which bands are best, and which combination of data and approaches work best. My advisors are Professor Stuart Finn, Dr. Anthea Mitchell, and Dr. Peter Scarth. My test site, let me get my pointer. My test site is the Injune Landscape Collaborative Project located in Southeast Queensland, as there is a wealth of historic data for this test site, and the vegetation communities in this area are typical of Queensland. And the potential impact of this project is to improve clearing and regrowth estimates that are used in numerous state, national, and international programs and initiatives. So why woodlands? According to Australia's National Forest Inventory, the structural requirements are that the mature stand height exceeds 2 meters and a crown cover of at least 20%. So we'll get to some more statistics later. But so this is what we're looking at, woodlands. When we look at all the forests in Australia, we're looking at this classification. Woodlands are defined as having 20 to 50% crown cover. And as we see here, almost 45% of Australia's forests are considered medium woodland and 25% are considered low woodland. So the majority of our forests here are woodlands, so very important to have a better understanding of how to map them accurately. And the photos on the right give us an idea of what these ecosystems look like. And just to give it an idea of the extent of woodlands across Australia, and specifically for my research in Queensland, so the green area we're looking at is native forests in Australia. 77% of this is considered woodland. For Queensland, for South Australia, 93% of their native forest is considered woodland. And, oh, sorry, that was for this slide. So this is the forest throughout Australia, and then 77% of that for Queensland is woodland. For South Australia, it's 93%. And then just to give another little note, a lot of this is lease-held forest, which we can see in the blue area, and purple is privately held forest. So very important to have accurate mapping measures so we can make sure that people are following regulations and compliance, breaking any rules. And as I kind of mentioned before, overall, 69% of Australia's native forests are woodlands. This equates to 91 million hectares or 910,000 square kilometers. It may sound like a lot, but when we think about the previous slide, it really isn't that much. Between 1990 and 2021, over 12 million hectares have been cleared and re-cleared in Queensland alone. And why imaging radar? So this is an artist's depiction of the biomass satellite, which will be launched hopefully sometime in the near future. And it will have, it'll be the first P-band satellite ever launched. So why imaging radar? So imaging radar is an active sensor. It complements optical imagery by providing almost all-weather capability. It has the ability to see through smoke, clouds, and at night, and provides structural information. The amount of backscatter that the satellite receives gives an indication of what type of target on the ground the sensor is interacting with, or the signal is interacting with. Figure A shows the what extent different wavelengths penetrate through a forest. I will mostly be working with C-band and L-band. And figure B shows the three main scattering types, surface scattering, volume scattering, and double bounce. And figure C just gives a kind of a comparison of C-band and L-band imagery. And the darker areas have lower backscatter, and brighter areas have a higher backscatter. And we'll get to some of these reasons in a second. But basically, L-band, as we can see here, has a longer wavelength. It's 24 centimeters on average compared to 6 or 5.6 centimeters. And the longer the wavelength, the more it can penetrate. So when we see the darker areas, we're seeing that the signal is penetrating more through this vegetation and interacting with the ground. This is just a list of some of the bands, the common bands, their wavelengths, and their applications. Again, I will be working with C and L bands, and I may work with S band, possibly, if I can get the data for that. So I'll mostly be working with Sentinel-1 and ALOS Pulsar, which is from the Japanese Space Agency. Novastar is also an option. This is just a little time series. So on your, this is an area in the Injun area in my test site. And this area is classified as the broad vegetation group 25A. And this just means that it's classified as open forest to woodlands, and it's mostly dominated by acacia forests, also with some casuarina or other acacia species. And so I'll just quickly play, maybe. Oh, maybe I need to change back to, there we go. So we can kind of see, like, and I did kind of filter out some of the major cloudy days, but you don't really have an issue with clouds here. Your main issue with radar imagery is when there's rainfall events. But if you kind of look at these two areas, you'll see, like in this agricultural area, you'll see changes in the green and the brown and the vegetation on the left, and you'll see a change in the backscatter. It'll go darker or lighter, as we just saw here. And then you can, it's very easy to see water bodies with radar imagery because of or surface reflectance. So why do we want to monitor clearing and regrowth? The statewide land and tree study is a methodology that is used across Queensland and New South Wales. And the outputs from this SLATS program provides foundational data needed for fire management, for projects working with the Great Barrier Reef, for land restoration, emissions, legislative and compliance detection, as well as many more. So it's very important to improve as much as possible the foundational data that is used for vegetation regulations and policies, and for when Australia has to report on its carbon for the Paris Agreement or other international initiatives. It's very important that we give as accurate as possible data. Currently, there isn't an accurate and reliable method for repeatedly mapping clearing and regrowth. Although SLAT's method has recently switched to Sentinel-2, it previously used Landsat, which is 30 meter. There's still potential for improvement using imaging radar. The current method does a great job, but it does use a lot of manual editing and human interpretation. It also does use some machine learning or some deep learning, but there is some issues with certain areas, notably sparse vegetation and regrowth. So I'm looking at clearing and regrowth, and woodlands are sparse. They're kind of spread out by definition. So these are two areas that can be improved. And this is just an area in northeastern New South Wales and illustrates what clearing and regrowth can look like in radar imagery. So the higher the backscatter, or higher backscatter, is represented by lighter colors, and lower backscatter by darker colors. So lighter, so there's some vegetation, or there's something there with structure, and then that's removed. There's less backscatter, and then same for over here. It's been shown that this is a paper from Dr. Mitchell, one of my advisors, which shows the utility of SAR in distinguishing structural differences. L-band in this scenario is better at distinguishing regrowth in eucalypt stations. And objectives and methods. So just to go over the test site a little bit, the ILCP, the In-June Landscape Collaborative Project, began in 1998 through an Australian Research Council funded 3-year project to evaluate the potential of SAR for forest structure and above ground biomass before the launch of the Japanese Aerospace Agency's ALOS PALSAR satellite. So this was kind of a testing bed to see what could be possible. This site was chosen partly due to the vegetation communities here. They're very typical of what you see across Queensland. So the site is a 40 by 60 kilometer mixed forest agricultural landscape. I have some more pictures coming up of that later. So in 2000, so this, let me get my laser. So this kind of just gives you a reference point of where it is. I'm here currently in Brisbane, and I think it's maybe 10 hour drive, something like this west. So in 2000, the NASA AirSAR mission flew airborne synthetic aperture radar over the site with C, L, and P sensors on board. There has been numerous missions to collect field and ecological data, as well as aerial and terrestrial laser scanners to collect LiDAR data. I'm mostly working with the data in the red square, but aim to work with more of the historic data once I can get access to it. And there will be another mission, I think, in July to go out and do some more aerial LiDAR as well as some field data. And this is a picture of Sentinel-1. Well, not a real picture, but so data. So right now I'm kind of in the exploratory phase of the data. I'm kind of starting from scratch. I'm getting all the data and I'm processing it. So the imagery I'm currently working with is Sentinel-1 data from 2015 to the present, which is at the moment 106 images. And the process of getting all of the Sentinel-2 image at the moment, and for the same years for the 2015 to 2024. And I've just gotten access to ALOS PALSAR images from the Japanese Space Agency. This is L-band, so longer wavelength than the Sentinel-1 C-band. I'm also using the SLATS data, the statewide land and tree study data, to identify known clearing and regrowth areas, as well as the regional ecosystem data to identify what type of vegetation is on the ground. And then hopefully once biomass and another SAR satellite, NISAR, once those are launched, I definitely want to explore those and incorporate those into the study as well. And so this is just kind of a general, higher level overview of these initial methods. So on the left is just kind of the methodology. So the idea for objective 1 and 2 is to explore different combinations and bands using optical and radar data and C and L bands to see what works best for identifying clearing and regrowth. And then on the right is just, this is just my workflow for pre-processing of Sentinel-1 data. I'm doing all of this in SNAP, which is the software provided by the European Space Agency. So again, I'm kind of in an exploratory phase at the moment. And this is my test site. It looks a bit like a paint by numbers picture, but this is the 25 major vegetation groups across the site, and here they are listed. And going by this zonal statistics extraction using the SLATs, no, not using SLATs, using the regional ecosystem data, which gives the vegetation type, and all of the Sentinel-1 images, I've extracted the median backscatter for the polygons for each of the major vegetation groups. And you can kind of, it's a little messy here, so haven't detangled it just yet, but this is just gives you an idea that you can, we'll see some graphs coming up, but you can still see a seasonality in the imagery. So each year you can, even with the backscatter, you can see seasonality of the vegetation. And yes, so the polygons of the same veg type were merged together, and the zonal statistics for each major vegetation group were extracted from each radar image, which was 1 image per month for 10 years. So looking at specific species, you can see seasonal change in the backscatter. So this is, again, just the exploration part. I think I have one more. The eucalypt. So one of the things that I'm working on is matching up the backscatter with each vegetation group in order to get an idea of how the backscatter changes with the type of tree species. This will play a bit more of an important role once I start working with the L-band data and I can understand how the two bands interact differently with the same vegetation group. And then for clearing, so this is the test site, and here's one clearing polygon, just to get an idea of what it looks like. So this optical imagery is newer. I just included it just so we can have an idea of what the site looks like. Is its backscatter profile, you could say. So this was flagged as a clearing polygon from August 2016 to 2017. So this is their reporting, the SLATs reporting period is from August to August. So from August 16 to August 2017, we can see a bit of a decrease in backscatter, especially when you think about the error plots that we just saw. So in this is a good example of how the backscatter can be used to distinguish clearing events. And in conclusion, the preliminary results show that publicly available C-band data provided by Sentinel-1 is capable of distinguishing seasonal variations within vegetation groups as well as clearing events. The next steps are to repeat this process on more areas with known clearing events, start pre-processing and working with the L-band data from the Japanese Space Agency, and start exploring regrowth. The original aim was to scale up my approach to all of Queensland, but this has been scaled back a bit because it's quite a big undertaking. So depending on how I go with the deep learning, I would still like to explore these steps 2 and 3. I'd like to thank my advisors, Professor Stuart Finn, Dr. Mitchell, Dr. Scarth, SmartSat, the Australian American Association, and the Japanese Aerospace Exploration Agency for allowing me access to the ALOS pulsar data. I guess normally you might put pictures of your advisors. These aren't them, but I just wanted to show this picture. When I found it, fascinates me. Like, I mean, not in a good way, but it's just very interesting that this is how a lot of Australia was cleared 50, 60, 70 years ago with 2 tractors and these big balls on chains that would just mow down the trees. Like no tree could stand in the way of those. And this will be the end of my talk. And this is just another time series over the whole test site. The Sentinel-1 here and Sentinel-2 on this side. That's it. Thank you.
Awesome. Thank you, Jason. Great talk. So you finished a little bit early. We've got a little bit more time for questions. I'd invite those in the audience to raise their hands. I see Brandon up first. Go ahead.
Yes. Hi, I'm Brandon. I work with deep learning and remote sensing data as well. I wanted to ask you about the backscatter changes during that felling event you mentioned. it was interesting to me that it changed slowly over time instead of what I imagined it would to be like a really sharp delineation. Why is that?
Yeah, that's very good that you saw that, and I didn't mention that was so in the slats data that has all these clearing and regrowth polygons. Each one has a designation of what the reason for this, and the one that I just showed is considered to be cleared for pasture. So it's not completely cleared. Not all everything was knocked down. It's just more of I mean, I wasn't there in 2015, so I can't say for exactly,
Sure.
but I'm assuming the cattle were let out and then they grazed quite a bit, and that reduced a lot of the structural, or the vegetation, which reduced the structure that the signal could interact with. This is why I want to find, so I've learned after doing this that my test site, well, as we saw in one of the maps, is quite small, and there aren't very many distinct like clear felling events where like trees are just cleared. But there are many around Queensland. So I could actually just show you really quickly since we have time. Yeah. Okay, so I'll just quickly show you. So I have identified clearing polygons all over Queensland. The issue now is I have to download and pre-process a lot of radar imagery for each one of those. Now I could use Google Earth Engine, but the issue is when I want to look at C-band and L-band data, and I'm not sure if they have allocation data because it's commercial data, and so, and also at the same time, since I mean imaging radar is new to me, my project changed due to COVID. And so now I'm doing this, which I'm still, I mean, it was a change, but I'm quite happy with where I am now and learning imaging radar. So doing all the pre-processing, doing all this stuff is a very good way of learning about the data and understanding it better. And yeah, so my aims are to, for example, there was a site, I don't know if I can.
Sorry, do you mind if I ask a follow-up question before
Sure.
you go? So you said that it probably wasn't a sharp event where all the trees were cut down, just parts of them maybe, and then areas where there was grass, and then the grass was probably eaten by cows. That was your description of that event. You also mentioned that C-band radar in particular, early on, it reflects off of a lot of the surfaces, right? So if the major part of the decrease there was actually grass being removed, how can you tell the difference between trees going down and grass going down?
Well, this is where you would add the optical imagery to complement. Again, I'm not an expert.
Okay.
If there's an expert in the audience, they probably have a better answer than I do. But so that's the part of where I'm still, I've got all the radar imagery from my side. And then I'm trying to I still have to get all the optical imagery on my side. So I can be able to tie a comparison between, I mean, if there's one single tree that goes down, that's one thing. Well, maybe this kind of answers your, maybe a kind of answer. I guess you can see my PowerPoint maybe?
Yes. Yes.
Okay. So, so in areas like the Amazon rainforest, like the canopy is quite homogeneous. And if you lose enough trees where the canopy is affected, it's quite easy to see that there's a change, and the backscatter will change because it's a very like definitive hole has been made, for example, if we're just kind of assuming. Whereas when you think about woodlands, kind of by definition, they're sparse and they're spread out. So this is why it's a bit more difficult to accurately map. Because it's kind of randomized pattern, it's kind of sparse. Yeah, so you'll have a tree and a tree, and then you'll have a shrub, or maybe you'll have a tree and a grass. And I'm not, I don't, I mean, with 10 meter resolution, I'm not going to be able to get like super accurate
individual trees,
data. The idea is to try to build upon, or actually just, currently there is no radar imagery incorporated in the methodology. And mine is to try to bring this in, to try to improve it. And then also tried to just explore, the use of C and L band for Woodlands.
Mm-hmm.
I don't know if that really answered your question.
Yeah, no, that's great. Thank you.
You mentioned the ESA Snap software that you used. Just curious, did you have any trouble accessing that software? Is it publicly available, or did you get special permission from ESA?
Yeah, it's publicly available. It's not the only way to do the pre-processing for the radar imagery, and you can also do pre-processing for Sentinel-2 imagery, as well as other radar satellites. It's freely available. It is sometimes a bit funky. I've been suggested to use some other Python stuff, but the good thing is it's supposed to be updated soon, and it's supposed to be better integrated with Python. Hopefully, in the next year, it'll be released. The problem is it was supposed to be released last year, so it keeps getting pushed back and back. But once it gets released, it'll be much easier, especially to use Python.
Right, that was awesome. Thanks, Jason. I really appreciate that. We'll move on to the next agenda items now. So the next speaker will be Luis Tsutsui da Silva, and I'm just going to pull up Luis's bio here in a moment. Okay. Now Luis is from University of New South Wales in Sydney. His project is, as stated here, semi-supervised learning for automatic improvement of onboard object detection models on small satellites. Lucas is a PhD candidate, and he completed his Bachelor of Computer Engineering from the Federal University of Mato Grosso do Sul in Brazil, and a Master of Computer Science and Computational Mathematics from the University of Sao Paulo, also in Brazil. His master's research was on lightweight classification models for resource-constrained hardware, such as low-power microcontrollers. His current research aims to produce a new class of intelligent satellite systems capable of automatically refining onboard object detection models on small satellites in orbit. So obviously something that SmartSat is very interested in. So Lucas, over to you. Thanks.
So thank you, Andrew, for the introduction. My name is Lucas Tsutsui da Silva. I am a second-year PhD student at UNSW Sydney. I'm doing computer science, and my research project is semi-supervised learning for automatic improvement of onboard object detection models on small satellites. And my supervisors are Professor Gustavo Batista, Yang Song, Taju Ching, and Will Hain. So my research project is an extension of another existing research project funded by SmartSat CRC P210. And that project focuses on developing onboard machine learning models for image processing in CubeSats. And in my research, we focus on nanosatellites and CubeSats, which offer a short development time and low production costs. However, they have a few limitations, mostly due to the small size to fit its equipment, such as antenna, hardware, and battery. Power is also another very restrictive resource, since they rely only on the solar panels installed in the satellite faces to capture solar power and recharge their battery. And communication is extremely restricted in the downlink direction, which is when we send data from the satellite to the ground station. There are many factors for this restriction. For example, the equipment cost and power consumption. We also focus on Earth observation missions, which consist of taking photos of Earth from the space. And there are some edge computing platforms for neural network processing that make it possible to perform image processing on CubeSats and nanosatellites, because these platforms have small size and lower power consumption. The idea is to use the machine learning model to filter the images of interest and send them to the ground station. And performing this task on board allows the satellite to reduce the data communication and the power consumption, because it's going to send only a few selected images. The existing approaches for onboard image processing follow the pipeline in this figure. In phase 1, before launch, we pre-train a machine learning model with some available data sets and embed the pre-trained model into the satellite. And then in phase 2, when the satellite is already in space, it captures images and uses the machine learning model to select those images that it's going to send to the ground station. And the ground station sends instructions and model updates to the satellite. And as I said earlier, the communication from the satellite to the ground station is very restricted. So now I want to explain in more details the phase 2, which is the phase that my research focuses on. We use the satellite to capture images from the Earth. These images are processed by the onboard machine learning model. And the outputs from the machine learning model are used to decide which images will be selected to send to the ground station and which the images that are not selected. So the images are separated into sets, the selected images and the not selected images. Then the set of selected images is transmitted to the ground station, and the other set is discarded. Note that hopefully the satellite is going to transmit less data than it collected. So this is how the existing approaches for onboard image processing in nano satellites work. And we can identify some problems with these approaches. For example, the onboard machine learning model is static, which means that it changes only if the ground station sent a new update. And also, these approaches ignore the set of images not selected for downlink. And it can produce a sample bias because we will never see the images in which the model fails, the false negatives. And to improve the model performance, we could think about using supervised learning, but it is not viable because it would require a large amount of labeled images, and we could only get labels for the collected images if we send them to the ground for manual annotation. And this is not viable due to the restriction in the data transmission for downlink. So to solve these issues, my research proposes to use both selected and the not selected images to automatically improve the model performance on board. In this research, we focus on the object detection task, and we assume that the ground station can send a few annotation of the selected images back to the satellite. Therefore, we can have a set of partially labeled images and another set of unlabeled images, which means that we can apply semi-supervised learning to train the model and improve its performance. We employ active learning to obtain labels for a few images, and using the labeled and unlabeled images, we can apply semi-supervised object detection to automatically improve the detection performance of the onboard model. And since this is a generic solution, we hope that it will help satellite applications that employ object detection regardless of their domain. And this figure shows the same pipeline for onboard image processing with the proposed modifications of my research. In phase 1, we specified the focus to focus on object detection tasks. And in phase 2, we send annotations from the ground station to the nanosatellite and allow the automatic improvement of performance for the object detection model. These are the tasks that we planned to develop during my PhD candidature. During the last year, we performed some initial experiments with neural network accelerator and domain adaptation for ship detection. And currently, we are working on making the SSOD methods more efficient in terms of training time, so we can execute them on the CubeSats and nanosatellites, which have a more restricted hardware compared to the server computers that we usually use to train these models. And during this year, we also plan to work on adapting SSOD methods for online learning, since the satellite captures images as a data stream. And for the next years, we aim to develop semi-supervised domain adaptation for nanosatellites and evaluate our methods on a CubeSat testbed. Now I'm going to present two problems that we are working on. If you are working with machine learning for a satellite application, you know that it is usually hard, almost impossible, to find a data set that has images captured by a similar sensor that you plan to use in your application. And you may have to deal with domain adaptation, which means that the images that you use to pre-train the model in phase 1, the source domain, they have different characteristics from the images that the satellite captures in phase 2 at the target domain. For example, as presented in this figure, the spatial resolution and the spectral bands can be different for different sensors. And these three figures show that some random images from shipped detection data sets that I'm working with. And we can see that they have clear differences. If we train a model using one of these data sets, this model may not have like a good performance, a good test performance on another data set. And that's what we did. We first trained the model with one data set and tested with a different data set. And we can see the detection performance usually decreases in the left part of this table. However, if we assume that we have access to the training images of the second data set, the one that we use for testing, and also we have access for only 1% of also only 1% of these images are labeled, then we can apply SSOD and get better results. This is another problem that we are working on, is how to make SSOD methods more efficient in terms of training time. We are developing a more efficient method compared to some existing SSOD methods. And the challenge here is to reduce the training time and maintain the detection performance. The figure in the right shows that our method can actually achieve a lower training time. but the detection performance decreases, as we can see in the left figure. And these are the preliminary results of my research, which means that I'm still working on it, trying to improve the results. And it is what is giving me headaches in the past weeks. With that, I finish my presentation, and thank you for your attention, and I'll be happy to answer any questions.
Thanks very much, Lucas. Great talk, and I must apologize for incorrectly using the wrong name when I was referring to you in the introduction. Apologies for that. So are there any questions from the audience? No questions coming through so far. I will just point out that, Lucas, you mentioned the Project 210, which is one of our main research program projects that I'm following. And I don't know if you mentioned it explicitly in your talk, but SmartSat is quite interested to demonstrate, algorithms coming out of 210 on the Kanyini CubeSat mission. Many of you would have seen in the news that the Kanyini was recently shipped to the launch provider. It's completed all of its ground qualification testing. So it's a really exciting time for that mission where SmartSat's hoping to get a lot of onboard research flying. And I can't promise you this, but I'd be pretty sure that getting post-grad students, PhD students, research on Kanyini would also be quite interesting to SmartSat. Brandon, again, I see a question from you there. Go ahead.
Hi, sorry, didn't mean to interrupt your flow. I just wanted to ask maybe a question about the setup of the problem that I didn't quite follow. What are you trying to detect with your objects? What are you interested in obtaining? Like, is it, you said ships, but also you showed buildings. Are these important? Like, who's deciding that these are important things to look at, and why are you choosing those things to look at?
Okay, thank you for your question, Brandon. So we don't have like a specific problem right now. We are using the ship detection to evaluate our methods on a satellite application, because these data sets, they have been used by the people that were working in the P210 project. So I followed them on that. But we are also going to evaluate our methods on the usual benchmark data sets for object detection.
You mean remote sensing object detection? Or general? Sorry? You mean remote sensing object detection? Or no, general computer vision?
Yeah. Yeah, because I want to compare my methods with the state-of-the-art methods, so I need to use them to perform like a comparison.
Sure.
Yeah.
So if I understand correctly, you are showing you haven't made any decision then on what objects necessarily it must be. You want to show capability for some kind of object, and then based on that, some further work, if you wanted to actually productionize it and make something that's used in a satellite, you'd have to make a decision then on what it is you wanted to be looking for. Is that?
Yeah, that's it.
Okay. Cool.
Okay, are there any more questions? Oh, Hannah. Thank you. Go ahead.
Yes, thanks for the presentation. I'm actually curious about one thing. Sorry, I got distracted in the middle, so maybe you already covered this in your talk. But so you mentioned that you want to do this on board. The processing will be on board. Am I correct with that?
Yeah.
So could you elaborate a little bit on sort of the spec of the computer that you will have for doing the, I would imagine, so you are also planning to do the training on board. So as new data comes in, you're going to update your training, right? Yeah. So what's the spec of the computer? Do you know?
Right now we have to do the decision later, but we have worked with the Intel Movideo's chip that it has on the Intel Neural stick, compute stick, because it is the same chip that they use on the Kanini, I think.
Yeah.
Okay, right. Yeah, okay. So I'm interested on like the memory that's available.
Oh, sorry, I don't have this information.
Okay. But because usually
Hannah,
that's important for that kind of processing, and
Yeah.
I'm just curious.
yeah, we
But-
have some information on that, Hannah, that we can share with
okay.
you. I'm happy to talk about that at some point.
Okay, sounds good. Yeah, thanks. Yeah.
And just for everyone else's benefit, Hannah is one of our professorial chairs at ANU, and I forget exactly what your chair title is. Hannah, would you remind us?
Sure, system autonomy, intelligence, and decision making.
Great.
Yeah.
Thank
So,
you.
so I'm more on the decision making side rather on the detection or perception side, but I can see that as like a loop, single loop. Yeah. Okay. Thanks.
Great.
For that. Yeah.
Okay, thanks. Are there any more questions for Lucas? All right. If not, we'll move on to the next speaker, which is William Damario Lukito. William will be talking about the topic on the screen there, and he's a PhD candidate at Trobe University, currently working on AI techniques for satellite communications and especially IoT applications. William completed his bachelor and master degrees in telecommunications engineering from Bandung Institute of Technology in Indonesia in 21 and 22 respectively. So William, the floor is yours. Thank you.
All right, thank you very much, Andrew. Okay, all right, greetings everyone. My name is William Lukito, and I am a PhD student working with Trobe University, particularly with the Cisco Trobe Center for AI and IoT. So basically, I just started my second year of PhD. So I would like to share to you about several outcomes I got during my first year of a PhD. But before that, I would like to thank SmartSat for the opportunity for me to present my work today. All right, so today I'm going to present a presentation entitled Pioneering the Future of Satellite IoT Communications through Resource Allocation and 6G Emerging Technologies. First, I would like to give a short intermezzo on what does 6G networks means and what is the relationship with Internet of Things. So in a simple word, 6G is the continuation of our existing and previous generation networks. And in the 6G, we aim for a faster data rate as well as a lower latency compared to the existing networks. And in the 6G, we have a target to integrate customer services and applications through Internet of Things. And with this idea, we are facing a future of fully intelligent and autonomous world. In the 6G networks, the connectivity speed is expected to be very fast, so that to imagine we will not need any loading bars anymore, regardless how big the data will be, because the speed will be very fast. Therefore, in the 6G, there will be no waiting time anymore. And this is also very important as one of the key performance indicators of 6G mentioned about global connectivity. It is somehow kind of opposite of the existing IoT networks, which is currently mainly based on terrestrial networks such as cellular networks, fiber optics, LoRa, etc. Therefore, satellite communications become a promising solution as satellites can offer a bigger coverage area. And by incorporating satellite communication for IoT networks, it is possible for ground IoT devices to directly communicate with satellite systems. So we have a terminology called direct to satellite communications, which is basically we directly communicate from the ground going to the space. However, due to the large distance and some environmental factors, the performance of direct communication link can be worse. Therefore, the transmission capacity also becomes worse. Okay, so before I go further, I would like to acknowledge my supervisors, Professor Wei Sheng as my principal supervisor, and Dr. Peng Cheng and Dr. Fulai as my co-supervisors. To date, they have supported me a lot through many feedback and discussions. Thank you so much. Okay, so regarding the project summary, initially our research project aims to integrate advanced technologies such as deep learning, reconfigurable intelligence surfaces, etc., to better improve the performance of existing satellite IoT communications in the direction of the emerging 6G network. However, after doing more literature reviews, I think it would be more interesting if we are able to unlock the potential of satellite IoT communications. For example, integrating sensing into satellite IoT communications. By doing so, the system will do multiple functions simultaneously, and yeah, we can save more spectral resources. Because of those goals, we hope that after conducting this research, we can propose a framework that is able to enhance the spectral efficiency, as the existing resource will be able to accommodate more users and functions. Therefore, we can achieve more efficient utilization of our limited communication resources. And we also want to share that we have finished paper, and we also have done the revision, and we are ready to resubmit our very first paper. Okay, so now as for the project timeline, basically we separated it into 3 parts according to the years. So during my first year of PhD, we developed an understanding of the system model, and we demonstrated a non-convex optimization to demonstrate the system model. And this consists of the deployment of 6G key technologies such as StarRIS and UAV. And we also considered a power allocation problem that is subject to high fairness level constraint without sacrificing significant cumulative data rate. And for my second year of PhD, we will do advanced resource allocation for ISAC framework of our satellite IoT network. And currently, we are aiming for a scalable deep learning aided phasive and ISAC waveform design. So basically, what we want to do is we want to implement the concept of learning to optimize and demonstrate that concept into the resource allocation for ISAC framework. And for the third year of PhD, we plan to do a particular task for ISAC of our satellite IoT framework. And my initial plan is to do a 2-dimensional sensing representation based on the received IoT communication signal properties. And yeah, fingers crossed that at the end of the third year, I'll be able to submit my thesis. So for the rest of this presentation, I will give an overview about the system modeling and the optimization demonstration of our proposed satellite IoT communications model. So to begin, we consider a direct-to-satellite IoT communication scenario where multiple ground IoT sensors are deployed on the ground. And when a line of sight link does not work, then a relay device plays an instrumental role to provide spatial diversity. And in this scenario, ground IoT devices will have 2 links to the satellite. The first link is the line of sight link, and the second link is the link through a relay device. And this is also very important to note that we are considering LEO satellites in our system model. Therefore, the satellite position is moving over time. And regarding the relay technologies, recently there is a cutting-edge technology termed reconfigurable intelligence surface, or we can make it short as RIS. So basically, RIS is capable to actively modify the wireless communication environment by reflecting signal and steering them towards a specific direction. And as for the satellite communication case, I think star rays or simultaneously transmitting and reflecting rays is more applicable because it has transmission mode, so that the signal can penetrate through the surface from the ground to the space or from the space to the ground. But the first question we have when we try to utilize RIS is what is the optimum configuration we need to do so that the star rays can achieve maximum spectral efficiency. So that is the very first question. And the second question is related to how we mount the star rays, as mounting it into a static position might not be optimum because of the dynamic nature of LEO satellite communication. And therefore, I think UAV, like deploying UAV, becomes a good solution as UAV can move freely in the air. But UAV is indeed a power-hungry vehicle. Therefore, UAV flight trajectory optimization is very important. Okay, so according to the previous explanation, we can formulate the problem. So in this problem formulation, we aim to maximize the energy efficiency by considering these following key questions. So the first question is how to determine an optimal UAV's trajectory plan. And the second question is how to optimize the star rays phasive matrix. And the last question is how to optimally allocate transmission power for all IoT devices. And we are going to answer this question by considering several constraints such as flying regulation and then minimum user fairness level and also discrete phasive constraint. And on the picture on the left side of the slide is the proposed star rays UAV for satellite IoT communications. So basically, we mount a star rays on the top of UAV. So we formulated the problem in a fractional form. So basically, the numerator of the fraction is basically the system throughput, and the denominator is basically the energy's UAV consumption. And these are the detailed constraints group. So the first group is related to the flying regulation. The second group is related to power allocation. The third group is related to the fairness. And the last group is related to the discrete phasive nature of star rays. So the formulated problem is non-convex and NP-hard. Therefore, it is extremely challenging to solve this problem mathematically or directly solve it. It is really hard. Therefore, we propose an iterative algorithm called ITPP, which is Integrated Trajectory, Phasive, and Power Allocation Design, to solve this problem. So basically, ITPP is designed under a Dinkelbach procedure, which is an iterative algorithm. So the advantage of our solution is it's easy to implement, and it is able to do simultaneous phasive optimization, and it can quickly achieve it can quickly achieve fair power allocation. Okay, so the workflow of our ITPP is, so first we have the initial problem, the original problem, which is in a fractional form objective. Then after that, we can convert it into a linear objective by utilizing Dinkelbach procedure. And after that, we solve the separated problem into three manageable subproblems. So the first subproblem is the trajectory optimization. So for the trajectory optimization, we first convert the UAV kinematic, and then we apply a greedy-based approach. And for the second subproblem, we adopt a simulated annealing-based algorithm to solve this phasive design. And for the fair power allocation, first we convert the problem into a game, and then we prove that the game is a potential game. And after that, we solve it with best response dynamics-based algorithm. And after this, I will show you some numerical results and comparisons. Okay, so we have 3 comparison schemes here. And regarding the result, firstly, the energy efficiency of our proposed sim demonstrates a non-decreasing behavior for each iteration. And as we can see here, it converges after 5 iterations. Secondly, compared to the selected baselines, our energy efficiency scheme outperforms other baseline schemes. And this is mostly due to the integration of the proposed Starry's UAV and the ITPP. While the Starry's UAV and ITPP both can improve the throughput, ITPP particularly contributes to the reduction of UAV energy consumption. And this is proven by looking at the energy consumption and throughput results. As we can see here, our trajectory optimization can save up to 40% energy compared to the unoptimized scheme. And we can see here that our Starry's UAV can gain up to 67% more throughput compared to the only line of sight communications. And as for the optimized trajectory, so here is the trajectory comparisons. So the optimized trajectory exhibits a smooth movement profile and remain within a designated flying boundaries. Therefore, this proves that our strategy does not violate the flying regulation constraint. But here, I also want to highlight that our optimization scheme can achieve almost perfect fairness without sacrificing much energy efficiency. So as you can see here, our last stage of optimization, which is stage 3, is already almost 100% of fairness. But when we try to see it from the energy efficiency perspective, we only have a very small decrease compared to the stage number 2. So I think this is a key advantage of our power allocation method. Okay, so regarding the power allocation itself, these results provides a clear demonstration of user fairness by showing the individual energy efficiency for each user. So in this case, we consider 8 users, and yeah, it also becomes evident that our power allocation, which can be seamlessly extended to all schemes, we can see that all of the user almost have uniform energy efficiency. This result also highlights that our power allocation can be easily extended to many system models. And yeah, since we considered a game theoretic approach in this subproblem, then we also need to consider about the Nash equilibrium. So this power allocation is a direct result of our optimization scheme that considered that game theoretic approach. And we also show that the Nash equilibrium of our fair power allocation can be achieved within a finite game iteration. So as we can see here, the maximum number of iteration is 25. So we proved that we can solve it within a finite game iteration. So what is next? So currently, we just started working on the integrated sensing and communications of our satellite IoT network as we aim to improve the spectrum efficiency. It means that we want to accommodate more users and more tasks over the same resource. So specifically for ISAC, the challenge is how can we effectively combine communications and sensing tasks within a common resource block with a minor performance trade-off. This is very important because intuitively, if we increase the priority of a task, then the other task performance will become worse. So here I put some very short preliminary studies. So I try to transmit both information, and at the same time, I also do sensing. And yeah, here is the very short demonstration that we are able to decode the data with BPSK modulation, and we also got the position of 5 targets at the same time. Okay, so to conclude this presentation, I list some contributions that we have made so far. First, we propose a new relying framework that consists of StarRIS and UAV to support satellite IoT communications. Second, we formulated an energy efficiency maximization problem and proposed ITPP to solve it. Third, we showed that the integration between StarRIS UAV and ITPP is key to achieve optimal energy efficiency. All right, so thank you so much for your attention. Any further discussion are very welcome. Now I return the stage to Andrew. Thank you very much.
Thank you, William, and great work for some very sophisticated analysis and research there. So I'd like to invite questions. If anybody from the audience has any questions for William, please raise your hand. Nobody yet. I see Craig Smith in the audience, probably one of the more people closer to this kind of research area. Maybe Craig might have a question. In the meantime, I would just like to ask William, have you considered what kind of industry partners might be interested in using this kind of research? I saw Cisco's on your slides. I guess they're a partner of your research group there. They're not particularly active in satellite communications, but are there any other industry partners that you think could leverage this research?
Yeah, I think the most visible industry partner that can work together with my research project is some kind of IoT satellite IoT operators. So any company that working on IoT service over satellite that can utilize the outcome of my research.
Yeah, interesting. And IoT is now.
I think it also can be extended not only to IoT application, but any kind of ground terminals that directly communicating with the satellite.
Right. And it's interesting now, really fast and developments internationally as we look at this so-called direct-to-device satellite communications, where LEO satellites are now starting to talk to handheld consumer devices, and that's really directly adjacent to IoT applications. Where just so everybody's aware, inside SmartSat, we're very interested to understand more about those trends and see how any of our research could be applicable there. There's a company called Safety from Space you might be aware of that's done some other narrowband communications projects with SmartSat funding. You might want to look up their work. That's probably our main thrust in that area at the moment.
Okay, thank you very much.
Yeah. So any other questions in the audience for William? Not seeing anything. Oh, Hannah, I see you have your hand up there. Go ahead.
Yeah. Thanks for the nice presentation, William. So perhaps a little bit more on the technical question. So you mentioned that you can get the nest equilibrium in the trajectory optimization. So I'm actually curious. In many cases in robotics, usually we then do an update every now and then. So basically, you have a feedback loop. And now one of the issue, if we rely on converging to a particular nest equilibrium, is that many of these games actually have multiple nest equilibrium.
Yes.
And so what ends up happening is that you keep on flipping between different nest equilibrium. So do you have that issue as well? If you do, what do you do to make sure that you don't keep on flipping, especially if you keep on flipping to totally different trajectories? That's usually not great.
Yeah, okay, thank you very much, Prof. Hannah, for the question. So basically, when we try to find out about the nest equilibrium for our power allocation method, we try to run it for every different time slot, and then we find the average. And yeah, as you mentioned, that different time slot will result on different nest equilibrium. And the one that I show in the slide is the maximum average nest equilibrium value, which is it just proves that our power allocation problem can be solved within a finite nest equilibrium. Yes.
Okay, thanks. Yeah.
No problem. Thank you very much.
Okay, so unless there are any other questions for William, I would leave it there and say thank you very much to William. I really
Thank you very
appreciate that.
much.
Okay, well, I think we'll bring this session to a close. Thank you everyone for participating, and looking forward to seeing you next time. Thank you, Tool, for organising.